We're gonna start with a little warm-up. And for that warm-up, we're gonna answer a simple question once there it is. Code is visible. And that is 12 a prime number? I mean, let's assume you don't know the obvious answer, which is no. How do we prove that 12 is a prime number? Proving that something is a prime is notoriously difficult, which is a good thing, usually, but for us that means we have a bit of work to do. So let's try reversing it. That's often quite a useful trick. Instead of proving that something is a prime, we could try proving that something is not a prime, which is a lot easier. To prove that something is not prime, you just have to provide a number that is not 1 and not the number itself, but still can divide that number. Easiest proof there is. You just have to find that number first. That's the difficult part. And if you can't find such a number, you can't prove that something is not prime, then it must be prime. So we still managed to prove it, just in a roundabout way. That means we have to find a number that can divide this 12. And the easiest way is to just try all kinds of numbers, from 2 to 11 in this case. Everything that's greater than 1 and less than the number itself. And for each number, just try to divide 12 and see if it works. And that screams loop for me. So we're gonna need a loop. Let's write that down for now. So we're gonna need a loop with something that does something. We wanna test different numbers. So we should have some variable that can hold the number we're looking at right now, that we're trying to divide a by, or 12. And let's use int d for division, which we're gonna start with 2, and we're just gonna count up. We're just gonna try 2, 3, 4, 5, etc. And that means we also have our condition, because we want to repeatedly test different numbers until we reach our initial number. So we do want to test our number as long as d is less than a. Our condition is done. And in here we definitely will want to increase d by 1. So something like equals d plus 1. That way we have a loop that will start at 2 and then iterate once, because 2 is less than 12, do something, increase d by 1 to 3, and then repeat the whole step because 3 is still less than 12, until at some point we hit 12, at which point the loop will end. Now what do we do in here? How do we show that a number can be divided by another? What does it mean in the first place? It means you can divide one integer by another, and the result is another integer number. So there are no decimal places left. It's not a point something, it's just 0.0, done. And if you remember the last episode, when you divide integer numbers, so if we, for example, would just divide a by d, the result will still be another integer. And if we try to divide 12 by 5, for example, well, the result as an integer will just be 2. Sure, it should be 2 point something, mathematically speaking, but since we're working with the integer data type, we'll round it towards 0. We basically cut off the decimals and we'll end up with just 2. And if we now multiply that 2 by 5 again, we get 10. And 10 is not equal to 12. So that's one way to go about it. We could try to divide our initial value a by d, and then multiply that result by d again, which from a pure math standpoint should result in just a. But because of the data type shenanigans in between, the output will only be exactly a if d can divide a. So that's one method we could use, but there's a simpler way. This is using two different operators. Well, technically 3 operators. We can reduce it by 1. Instead of a division, we use modulo, the percentage sign. I'm not quite sure if we talked about that last time. I think we did. I'm not too certain anymore, so I'm just gonna repeat it just in case I didn't mention it. Modulo is giving you the rest in a division. So let's say 1, 2, 3, 4, 5, 6, 7, 8. Let's say we make a division by 4 and we have a modulo by 4. So divided by 4, integer divided by integer, this would be just 0, 0, 0, 1, 1, 1, 1, 2. Now let's put a 9 in here. That's what we discussed last time. The old decimals get cut and it will just round, well, down in this case, but more accurately it will round towards 0. With a modulo, you don't get the result of a division, you get what's left after you try to divide the number. It asks the question, if you try to fit in this number into this other number as many times as you can, what is the number that's left over that you can't fit a full 4 in anymore? It's 1, 2, 3, 0. 1, 2, 3, 0, 1. So it's cyclical, it's just counting up towards 1 less than the number, and then it starts over at 0, if you just look at the numbers on the left rising. That's the modulo. It gives you the rest of the division. Division tells you how many times does this number fit in this other number, and this tells you what number would be left afterwards. And so if a number can divide another number perfectly, then the result will be just 0. There is no rest, there is nothing left over after you split it into parts. And so with a modulo you can test if a number is divisible by another, just looking for it being 0. Alright, so let's write that down quickly. That's not d. It was a divided by d, or actually a modulo d. If it's equal to 0, we should write in front if that's equal to 0, then a is divisible by d. Let's make it a bit bigger here. And in that case, we know a is not a prime number. We found a number greater than 1 and smaller than a that can divide a. So if this branch is reached, a is not a prime number. If it's not divisible, which we assume, if this is a prime number, well then we'll just increase d by 1 and try again with another number. Alright, we're close, we're already halfway done. What do we do when we found a number that can divide a? Problem is right now, if we find a candidate that does divide a equally, or does divide a properly, then we do nothing and we'll just repeat the old step without changing d. So we just try the same number again, have the same result and try the same number again. This would be an infinite loop. We have to somehow cause the loop to end? I mean, in theory, you could just increase d anyway, but that would have consequences. If we increase d anyway, then we would get the information that a was divisible by d, but then continue on and try another number, which wastes time. We already know it's not a prime, we don't need to check anymore, but it also we lose the information that we found a candidate, or we found divisor. So we have to keep track of that somehow, and ideally we stop the loop altogether. Because why continue searching if we already found a divisor? Well, how do we stop the loop then? Let's try it that way. We could do that by simply saying d is now equal to a, for example. That will definitely stop the loop. I mean, we still increase it by 1, but doesn't matter, d is now no longer less than a. The loop will definitely stop. So that's achieved, but we now lose the information which number divided our a. We can technically still figure out that it was a prime number or not by looking at d. If the loop ended simply because d was no longer less than a after we made this call, without this branch ever being reached, then d must be equal to a. If this branch was never found, we'll just slowly creep up on a until we exactly a. But if we reach this branch, then d will already be a when we increase it by 1, and so when we leave this loop, d will be greater than a. So based on the comparison between d and a, we can check if we found a number that can divide a or if it's a prime number. But that leaves us the information which number can divide it, which we might want to keep as a proof. Or maybe we do something interesting with it. Who knows? So that's not a good idea. Something else we could do, we could introduce another variable called p, which is a boolean this time, just true and false, and we're just gonna assume our number is a prime number. P, standing for is prime, is starting out as true because we assume a is a boolean, a is prime, and if we find a number that can divide a, we will say p is now false. So now we didn't need to change our variable d, we changed this other variable p. The value of d is still preserved, so to speak. But now this condition doesn't apply anymore, so we have to change that as well. We have to include our variable, so this is now a and p. So only as long as our counter variable d is less than a, as long as we have still candidates left to check, and as long as we didn't find a candidate that did divide a, continue this loop. And either we reached the end of our line, we tested all the numbers, and we fall out of the loop, or we found a number that can divide a, in which case we also exit the loop. And so after this loop is done, we can look at the boolean p, which is either going to be true if it was a prime number, or it was false if we found a number that can divide it. So a very simple boolean that can be used in an if statement, for example, to quickly check or to quickly change the behavior towards was it a prime or not. Also, variable d is now somewhat preserved. If we reach this point where p is set to false, we will still increase d by 1 before we drop out of the loop. But that means we can just remove 1 from d, and we'll have the original number that was able to divide a. So we can still get our variable back. Good, that's good, right? And yeah, in theory it is good, it's only having a second variable is a bit annoying. Oh, just a heads up. Yeah, of course, we could use an else here. In that case, we don't need to revert D anymore. I mean, we'd still drop out of the loop, but D would still be the original value. We don't need to subtract 1. So yeah, we could do that. I just didn't bother. I'm bothered by this extra variable. If you remember when we talked about if-else, I started by having a temporary variable to make our life easier, to make something possible that is not possible in the structure as it was, with the if. We used a bool to recreate the behavior of an else without having else. And in the same way, I'm using a bool right now to recreate a behavior that we can get another way. We don't need this variable. We don't need to check for it here. We don't need to set it here. Because there is a keyword we can use that has a very special meaning. This keyword is break. And you can think of it in two ways. You can either think of it as we are breaking out of the loop, or we're hitting the brakes when we're repeating constantly, when we're inside a loop. Because what break is doing is it immediately stops the entire code block that is associated with the looping behavior. If you have the keyword break, the next loop it finds, the next higher loop that exists, will be exited immediately. We immediately jump down here. All the other code in the loop is ignored. We just stop everything. We leave the scope, done. Nothing happens anymore. That is break. We break out of the loop. We're hitting the brakes to stop the loop. You can put it any way you want. If you have several loops, so if there was another loop up here, it would only apply to this innermost loop. Just a heads up. And the keyword break is used in other cases as well. It has other uses, but for now the one important one is it will stop the loop immediately. And well, it's an instruction, so we can also remove the brackets. With this, we have a very simple loop. If we ever find a value for D that can divide A, we just break. We end the loop and immediately end up down here. There's no more increasing this variable, there's no more checking the conditions up here, it doesn't matter. Anything that follows after doesn't matter, the condition doesn't matter, we just end the loop. Done. In which case, D will be still the value that can divide A, if we found one, or D will be exactly A if we exit it because this condition no longer applied. Oop. What happened? I think it was, yeah, I switched sides. Okay, that's fine. So we can still tell if A is prime or not by just checking if D is equal to A. If D is equal to A, then we have a prime number. If it's not A, then it will be less than A and it will be able to divide A. So we can verify the result we need to. This is a very straightforward, very simple way to check for a prime number. And yeah, it's very much brute force. There are faster methods, way better methods, but this is one way we can go about it. Let's say I want to test other numbers for being prime. Instead of 12, I want to check if 13. Just plus 1. Check the next number, if that is a prime. Our program right now is changed, it will work. Actually, let me close it up here. Whatever. It's going through all the numbers. It will, unlike with 12, not find a value for D that can divide A, and so 13 is a prime number. Nice. But I had to rewrite my program. What if I want to test several different numbers? Well, I mean, we already did something that tests different numbers. It's called a loop. We did it in here, so I presume we could just make a larger loop around this whole thing that will try different values for A, and for each of these values for A, it will run this inner loop to test different other numbers that can or cannot divide this current value of A. And that way we can test for prime for different numbers. But that would be one large loop that constantly tests different numbers for being prime. But what I'm talking about is at random points in my rather large program that I'm just theorizing about right now, I want to test a very specific number that is not related to the other numbers before or after. And there's a lot of other code that happens in between these moments where I need to test something for being prime. If I put everything in a large loop, I could certainly try to make it work. I could repeat the code, and I could have if blocks for everything and some Boolean values that would allow me to control which parts of my code get repeated when I repeat the entire program. And so I could say that everything except my prime test is ignored or skipped when I repeat the loop. And then after my prime test is done, I change some variables, some Boolean values, so when the loop repeats once more, my prime test is ignored and some other part of my code continues. That is certainly possible. You can, in theory, write a program like that. But it's a lot of work. And there are a lot of things you can't do in that case anymore. And it's just so unnecessary. Because we had this situation before. If you remember the assembly language, our loops and our ifs in here, they're just jump operations. They just let us jump back to a previous point in our program or jump forward, skipping a part of our program. But it's just jump operations that move back and forth in the entire list of code and memory. And towards the end, I didn't go into too much detail with that, but there was a very special kind of jump operation that didn't just have the purpose of jumping. And I don't mean the conditional jump. I mean the jump operation that did bring us to any point in memory we want, but allowed us to memorize from where we jumped. Which means we are able to jump back to where we originally came from. So instead of statically going forward or backwards, we could go to anywhere in our program and then right back to where we came from. And we can do that from anywhere to the same point and back. No problem. So what is that music? That's horrible. So with this, we were able to write a piece of code in the assembly language that we can reuse several times throughout our program without writing it again, which was very important for us because we had only very limited memory space, so reusing as much of our code as we can is paramount. With C#, we have, of course, modern computers to run it on, and memory isn't that hard to come by anymore. So, I mean, okay, it's getting more expensive, but still, it's magnitudes more than we had with our assembly. But still, we want to reuse code. If not for memory constraints, just for convenience, because we don't want to write the same code again and again and again. This concept, we called it functions, and that is a larger term that is used in many different languages, functions. But in C#, it has a different name that you will find for it. It is the same thing, it's just a different naming. Methods. So functions are methods, and C# uses the term methods to describe functions. It's the same concept. Methods are, if we simplify it, just instructions as a simple package, like one block of code. If you think about it, we have code blocks like here, which have a little label on top that tell us that this code block has conditions to run it. In this case, it's a loop, so this code block contains instructions, actual stuff to do that might get repeated. And with the if, keep in mind, this is also just brackets we are able to leave out in this case, but they are there. This is also just another code block with a label on top that says we can skip this potentially based on some conditions. With methods, we do essentially the same on a larger scale. We have code blocks. We add it here, we start it here, and we give them a label to mark it as this is a method. This is code that isn't triggered normally by just running the program straightforward. And this actually taps into another topic that will come at a later date. What we've done so far is we wrote code blocks that can contain instructions or other code blocks which themselves can contain instructions or other code blocks. But we're always starting with this curly bracket that starts our code block. And we just nest everything in there and go down and down, down, down. C# actually also grows in the other direction. There is something more outside of this code block that we're ignoring so far. And the first next layer that comes above us is the method. In fact, there's not just one such code block. We actually have several code blocks. And we're just gonna drop this. I'm just gonna rewrite it later. Let's simplify this maybe. Once we look at a C# program from a bit higher up, so to speak, we see that our code is not just one continuous list of instructions, the way we're used to it by now. It's actually split into several groups, seemingly independent groups of code blocks that don't have a strict guidance for execute this, then this, then this, then this. It's more of a collection of different programs, you could say. At least the way we saw programs so far, each method itself is a miniature program. And you call these miniature programs, or execute them, run them, perform them, when your main program is running. The actual thing you start on your computer. We've so far just assumed we are running inside a method that was running. And in fact, there is a very special method actually that would apply to. And I'm gonna pretend that method doesn't exist and we just have this one code block that we just start our made up execution right now. But all the other methods now will get properly defined, the way a method should. And that starts with a name. Actually, let me write the program from earlier. Once again, here, we had the daily. Let's just write the exact same program, just a bit more compact. While b less than a. If a mod d is 0, then break. Otherwise, d Well, let's shortcut it to D++. And then we're done. Just a reminder, D equals D plus 1 can be shortened to that's good. Plus equals 1. And that can be shortened to plus plus. Just a reminder. So this is a bit shorter. Now back to the topic. Methods have a name. Just like variables need names so we can identify them, so do methods. A variable name for a variable is a label we place on a specific location in memory where a single value is stored. So this name, this text we define, refers to a specific address that has one single value. That's a variable. A method has a name that also targets a specific address in memory, but not for a value, and instead where a block of code starts. So it's actually targeting a larger amount of memory, but it's containing only instructions, code that we want to run. Now I'm gonna call my method. No, that's not. Let's go simple, check prime. Like that. And you note that I have an uppercase C here. My variables are usually in lowercase. The method names are in uppercase. That's not necessary, that's just a coding convention, and it's the one I use, it's the one I'm familiar with. So this method is now called checkPrime. And using this name, I can run this code from other parts in my program, in my larger program. So I might be executing this code right now, just the way we learn it, instruction by instruction, line by line. I could just make a call to check prime. I can use the name, just as I can use variables. I can just use the name to tell the compiler I'm interested in this part of memory now, this code here. Please execute this code that is stored at check prime. And once you're done there, you can continue over here in my original code. With a variable name, I reference a value in memory that has to be used. So int f equals a plus 1. In that case, I would have to look up a in our table. Let's go back to that. Type, name, value. Right, I would have the table int a12, and for this calculation I would have to look up a. I go to our table, see it's 12, answer 12, make my addition. That's stuff we talked about already. And I see the value is hidden, right? So in here that's just saying value. Okay, let's maybe put this down a bit. Should be that high, should be fine. Okay. Type, name, value, like that. And a 12. That's what we do. That's what we do with a variable name, with a function name or method name. It's pretty much the same, only we don't check in our table. There's a, how do I say this? In a simplified term, there is a sort of lookup. Think of it like the table. Just this table is generated when you compile your program. It's not generated during runtime. It exists as part of your program. When you start it, it's just payload that exists. And that's just a list of names and addresses in memory, if we put it simply. And that hidden table that you don't interact with really tells the computer check prime has this address in memory, and that's where you can find the code to execute. So check prime, in a way, acts like an operator. Because if you think about the operators here, we do modulo operation, we do comparisons, we do additions. We're doing just the bare minimum. We just tell the computer we want this thing to happen, this abstract thing, but how that actually works is entirely up to the computer. We've talked about that already. Abstractions, higher level language. So what actually happens in the computer, what instructions have to be executed, what the actual code looks like, we don't know. We just know we want to call the modulo. We want to operate on these two values using the modulo operation. And same way we can use our methods. They are in a sense the same way. We just tell the computer we want to run this very specific code. Just we don't use any symbols for that, we use the name. But in principle it just tells the computer go to this other location that has instructions for you to follow and do that. It's just that these instructions are also written by us and not predetermined by the runtime language, by the computer or by whatever system you're using. And similar to the operator, there's something missing here. Just the name in of itself isn't going to help us much. Right now, check prime is testing if 12 is the prime number. I don't want to check if 12 is a prime number. I'm going to check if, for example, my 13 is a prime number, or a 2, or 521. And somehow need to get a number that's up here down into this A. How do we do that? Well, the most direct way doesn't work. As you can see, I have an int A up here and an int A up here, or down here. They are in different scopes. If you remember scoping, code blocks, we start a code block here that ends here. All the variables that are declared inside this area only exist inside this area. Same down here. We have a code block, curly bracket up here, curly bracket closed down here. Any variables declared in here only exist in here. So we can have an int A up here and an int A down here, and those are entirely different scenarios, different contexts. So we can't just declare a variable and it will be visible to the other. What we need to do is similar to how these operators work that are already built in. These methods in a way. We provide values when we make the call, when we request this operation. And different operators require different values. Like this one requires 2 integer values. This one requires also 2 integer values. This one requires 1 integer value. This is the next part we need to add here. Besides the name of our method, we also need to define what values a method needs. And we do that by adding normal brackets right after the name, which makes the whole thing look a bit like the blocks we already seen, like an if or a while. Only we don't add a keyword in front. This is completely made up by us. And inside these brackets, we don't put a condition anymore. Inside the brackets we add here, we need to close it as well. we'll add variable declarations. We declare the variables that we need, which means we provide the name and the type of, for example, int a. We do a full declaration, the type and a name. And that way we define check primes as requiring one integer value, which for the purposes of this method are referenced through the name a. And up here, we also have to add brackets. Inside those brackets, we now have to provide a value. We don't declare anything. What we do here is kind of the initialization step. We assign a value now. So I could put a 12 in here. Closing bracket. That's one thing I could do. Or I could provide a. Our a from up here. So when this operator is operated, is run, call, executed, we do the usual. We look up a in our table to figure out it's 12, and then we do the operation using the value 12. So we can provide an a in here, but it's still a separate a from this one. And we can also do full sequences of operations in here. That's perfectly fine. But this is probably the closest to what we want right now. We provide a to this method check prime, which will cause the computer to look up 12 and then provide 12 as a value for this operation. How does that look like now? The computer starts interpreting this instruction that follows down here, which, by the way, it is a fully functional instruction if we just add a semicolon. We don't have to add the semicolon here. We can do other stuff as well. We can, in theory at least, we can do other stuff. But for now, this is a fully functional instruction. When the computer tries to break this apart, it will see check prime and understand this as an operation, a method call. And when it performs the operation, it will pause everything else inside this code block, even in this instruction, and first execute this code. And only once this code is fully done and finished, this miniature program is completed, only then will the computer continue with this instruction up here. It will freeze the execution of this instruction completely until this is done. It will make more sense when we see example in a minute. What this function or method call then does is it will create a new table, which you should expect. We enter a new area with new curly brackets, but this is a bit different from what we are used to so far. See, these tables, they don't have infinite length. In fact, they are very limited in length. Or, well, not length, maybe in depth. The amount of rows we have in these tables is predetermined. If you think about it, how many rows do these tables need? We need one for each variable. So only one for each declaration in our code. Okay, mind if I were to make a declaration in inside the loop, for example, it will still only be one declaration. Once we leave the scope of this loop, the second table would be gone, and we repeat the loop and start a new table and only have that one declaration. So it doesn't matter how many loops there are. The number of declarations you can see in the code is determining the maximum number of rows we need in our tables. So the computer knows when starting the program exactly how long this table is going to be, how much space is needed. And after leaving exactly enough space to run the program, it will make a cut. This is where that range ends. This program up here, this method up here, gets exactly this amount of space. Not more. not less. Exactly that amount. 1 row for now, because we only have one declaration in here. When we now call this method check prime, it will look up how many declarations are inside check prime, how much space does this table need. And it will reserve exactly enough space in memory for this method. It will create a new table. Type name value. And this one is a bit larger than this one, because in here we have 2 declarations. We have one in here, and we have a special one in here. This counts as a variable declaration. And because it's special, let me just make a separator in here. When this table is created, this variable is already declared. Before we even start running this code down here for this method, before we even enter this part, we already have a table with int a. And it's not just a variable declaration, because we actually have a value in here. It's not undefined. We fill this table with the variable declaration that is part of the definition for check prime, and we give it the value. We immediately assign the value that was provided in the call itself. And when we called this method, we already referenced a and found out it's 13, so what we give in here is 13. This first line, this definition for the method, is now done. We have a table and we have already a declared and initialized variable a. And only now do we enter the actual code. We already start with a pre-filled table. And now we can run this code like normal. We have an int d, which starts off as nothing and then is filled with 2. And then we have this loop which will check conditions, and we do a lot of things in here, constantly updating d, until at some point we hit 13 and this loop exits, and then the entire method exits. This miniature program stops. At which point all of this is deleted. And we continue our program up here. So let's try to play that out once more. No, why did I write 12? It's 13. That was nonsense. We start our program up here. And we start off with this instruction, int a was 13. 2 operations, we declare a variable, we assign a value, we declare the variable first, no value, then the assignment, we assign 13, and the instruction is completed. Then comes the next instruction, check prime. Check prime a. This is one operation, this method call, but there's the hidden operation, so to speak, the lookup for a. So what we actually have to do is look up a first and check prime 13. Now here comes the weird part. We don't complete the operation yet, or we don't complete the instruction yet. This operation has to complete first before we can finish the instruction, just as we have to wait for any other operation. It's just for the usual operations, we don't see anything happening, so we just pretend like it's instant resolve and it's done. But the computer does take time for that. And during that time, we'll just stay at this point and wait for the computer to return. And the same happens if the operation is defined by us. This check prime is getting called, and while we wait for that call, we just keep the context running. We just keep this instruction in its half-finished state and just put that aside. We just remember we are at this point. We just, okay, remember that. We move on first. Let's make some lines in here. So this is the working area, so to speak, for our first method. And since we called this operation, the computer will reserve the space necessary for this method. That means a new table. With 2 rows, and well, there's, to preserve our context, we have a little working area with stuff. But as I mentioned, there's a special table here because there's a special declaration which already received the value 13. We run this operation using the value 13. The computer has to prepare a few things in memory first before the operation can run. That is, providing the value in the manner it was declared in here. So we start with this table, int a equals 13. And now we can run the operations. So int, well, the different instructions. Int d equals 2, int d, the declaration, d equals 2, assignment. So instead of undefined, it's now a 2. Right, and then we check the condition, d less than a. We resolve d to 2 and a to 13. We perform the operation, 2 less than 13, which is true. So this condition evaluates to true, and we do get into this and we evaluate the next condition, and the whole process continues until we stop in here. The method is done, code is completed, and then the computer will just drop everything that's in here. It's gone. And we continue with executing this instruction up here now. As if we waited for an addition. We just didn't wait for an addition, we waited for this method call. And since this method call is now done, this entire instruction is done. And we can move on to the next instruction. You might notice an issue we have right now, after I take a drink. We do, in fact, figure out if a value is a prime number. This method we called did notice we don't have a number that can divide 13. So 13 is a prime number. Cool. We don't know that up here. We did call the method did its job and did it correctly, and we know the method is done because our code continues, but we don't know the result. We don't know if a is a prime. Could be not. We don't see it. Again, we have no access to the data down here. Especially now after we deleted the tables, we have no more way to check what happened in here. Let's think back on operations. These operations take in values, but they also return values. We have a symbol for the operation, which is a collection of symbols, a name, and we have a way to declare variables in here. We can define what data the operation requires as input. The only thing we're lacking, the third important component for any method, is the output. We have to somehow tell the computer what we expect this method to return as a result. And we put that in front of the name, so I'll just move that aside. And what we do in here is, in a way, we declare a variable again, with the method itself being the variable. So we start with a data type. We want this to return, well, we could do two things. We could just return a Boolean to say, is something a prime? But it'd be much more useful to actually use D. That's what we wanted earlier, right? We wanted to have the number that can divide our input number. So we can verify the proof if we need to. So we want to return an integer value. So we, in a way, declare a variable called checkPrime. Only checkPrime is not a variable, it's a method. So we add the brackets and declare variables that serve as the input for our method, for our custom operation, checkPrime. So checkPrime is a method that receives an integer and it returns an integer. And that means up here, we can change our code to this. Let's clean this up a bit. We need some more space because now we have two declarations. Our table has space for 2 rows now. So we have the working area. This method, when it's called, will receive a value from us, an integer, but when it's done, it will already also return a value. Just like any operation has an end result, so will this. So when we end up down here, let's simplify this. So int d equals checkPrime, prime a. Well, first have to resolve. So the method call has priority over the declaration and the assignment. So we start with a, resolve to 13, int d equals checkPrime 13. And now the method call. So we pause in here and we go to the method. We see we need 1, 2 rows for our table, and our table is pre-filled with one integer value, the 13 we got here. All right, so we create in this new space that is reserved for this method only, new table. Value. Let's, yeah, no, that's fine. And actually, let's make this a bit bigger like that. And we start by adding the declared variable a and the value that was provided from the call side, 13. And now we can start this program, starting by check for int d, setting it to 2. Then the variable comes in, and of course this is a code block, so there is a new table that gets added in here. Not value, name value. Just the way I showed you with scope, there's a new table. It's just that this table is empty. There are no rows in here because nothing gets added. So technically the space is there, it's just the space is 0, because we don't need it. But the new tables we add with the new scopes are added below this table, not in a third space. These chunks here are unique for each method. And within a method chunk, block, segment, we can have several of these tables for each scope. So we do our thing here, we test all the numbers, figure out nothing works, and we end up with a 13 in the end. how do we now get this value for D that we wanted to return back up here? How do we tell the computer that this D is what we want up there? For the input, we just put the value. For the input, we just put the value in here and define the receiver down here, the method arguments. For the result, we have to use a special keyword. So as last action, so to speak, down here, after our code is done, we'll use this new keyword, and it's called return. Return has a very similar meaning to break. A return means that no matter where we are in our program right here within the method, we'll stop everything and immediately go back to where we came from. Return to sender, return to caller. And so this return, this could be up here already. We could put a return right at the beginning. The very first thing we do is a return. This is valid code. It would ignore everything else that happens in here. But we could do that. Just like a break will immediately abandon everything inside the loop and shut it down and jump after it, a return will immediately stop the entire method it is in. Same principle, just on a different level. And this return is also the mechanism by which we define what value goes back. We return, but not empty-handed. We return with something. We return with D. You can imagine it a bit like return being a hidden variable in a way that you assign a value to. Only there is no variable called return, it's just the keyword. We don't assign it, but maybe that helps you memorize it. We return, and we return with a value in hand, namely the value for D. When we hit the return, we look up D. We can have full math in here, by the way. Like we can do full operation chains, almost an entire instruction in a way, before the return. The return is the last thing that will happen. It is the lowest precedence. It's an operation in a way. When we look up D, it's 13, so we return 13. And just like up here, where we made a method call using a value to go down here, we now have a result, and we return. When we return, we delete everything that's in here. It's gone. And return up here to where we made the call. The operation is complete. We have a result now. And we replace... Or actually, no, we don't replace in a way. Undo. We set the value now in here. As if this was a variable we just looked up. Or maybe an operation using two variables that had a result. And that result was a 13 that is now in here. So we can now perform the declaration int d, which starts with nothing, and then we make the assignment d equals 13. And with that, the instruction is finally done. This is how we can do a method call. And we can do that again. We can do d equals check prime. for 521. No problem. It will do the exact same steps. It will call the operation. No lookup needed this time. So we create a new table in here, pre-fill the special variable a, declared variable a, with the value 521, and then we start executing the instructions inside this code block. And then by the end, we will hit the return, which has a specific value associated with it. And so we take this value, we drop everything that was associated with this method except for this value. We go back up and use that value as the result for this method call. Now some specialties. Check prime right now requires a simple integer input. It doesn't need one. We can have a method with no argument at all. Let's say maybe it does only check hard-coded for 12. That's fine. We just remove the value in there and we leave the brackets in here empty as well, but we do have to add them. Empty brackets for no arguments. We can also have several arguments. For example, this could be a2 if we wanted first a, like before, but we wanted a second value as well, int d. We just use a simple comma, not a semicolon, comma. In here as well, a comma, not a semicolon. We basically just list declarations, and here we just list values. And now we start this method by declaring a table with two variables already pretty much finished. We declare them, we initialize them with the values we get up here, and then we start executing the code. That's perfectly fine. So you can have any amount of arguments. 0, 1, 2, 3, 4, 200. I mean, that gets a bit silly, but it's possible. I'm sure there's an upper limit somewhere. Maybe as a sanity check of some sort, but I'm not sure what that limit would be. I'm not keen on finding out. But yeah, that's doable. On the other end, our method right now returns a single value, an integer. There are methods that will be used a lot later on that are quite useful on their own, that don't return any values, that don't have a result. Those methods do something, but you don't get any feedback from them. And with our program so far, that doesn't make much sense. They get useless. But they will become useful later on. And for that special case where a method does not have a result, it doesn't provide a return value, that is a special case, even though they are very, very common. You can't just leave out the data type. With the arguments, you just leave them out and it's done. You just leave it empty. No problem. But with the return type, you have to provide something in here before the name. You can't just leave that empty and not define a data type. For that purpose, there exists a special keyword, which is actually a special data type. You can think of it as a workaround, maybe. Like someone wasn't sure how to make this differently, so they just added a special data type that has a very special meaning that is understood by the computer and doesn't really do anything. It is useful in other cases too, actually, that data type, but let's not talk around it. This type is a void. VOID, void. This is a special keyword that marks this method as I don't have a return value. And because we don't have a return value, this return down here is also wrong right now, because we give it a value, but it doesn't return a value, it cannot accept anything in here. So we just drop it. We just have the return on its own. And if we just have a return right at the end of our method without any purpose, we can also skip it. We don't need to add it. It is technically there, but the compiler does it on its own. Just as the compiler adds the curly brackets in here for us, it adds the return statement also for us. We don't need to write it out, but we can. And of course, we do need to do it if we switch page again, if we want to return at a different location earlier. So if I return to my original code maybe, let's put an int in here. And I want to return D. I could do this return in here already. Instead of a break, I could do the full return. Because it is effectively the same thing, just on a larger scale. Again, return means drop everything, this entire method, and just go back to where we came from with this value in hand. We don't just exit the loop, we exit the entire method. So this will immediately jump back once we found a number that can divide A. We still need this down here, this return though, because if this branch is never reached, if we never find a number that can divide A, if A is a prime number, we still have to return something. And we could return D, but of course at this point we could also just return A, which should be the same value, at least if our program worked correctly. Or it could also be slightly off and say it's 1. Or maybe 0. It's for you as the programmer to decide how your method behaves. In our case, just break in here and return D down here. That's good enough. It's very simple to understand. And you have a very consistent behavior for how the values get returned. But it all depends on your context, of course. Now keep that in mind. This is a method we wrote. This up here is also a method we wrote. You don't know what its name is, and you don't need to know for now, but this could be in fact another method. We can have as many methods as we want. And prime could, for example, do this. We declare a new variable. We have int prime as a new method. We declare a variable int, it's called p. And then inside, what we do is combine a few things. Return p equals, no, not equals, p less than check prime, and that will get p and 2 with our code currently, and we close it up. And instead of all of this up here, we could have, oh actually we don't have an int in here, this is a bool. And we can then write code up here, which is prime a equals 0. Look, nonsense, but it works. So our code up here will, when executing this code, call prime using the value for a, and prime itself will internally, when executing its return function, or return statement here, First, evaluate this entire statement, this part of the instruction. It has still the less operator in here and this method call operation. And it needs to first evaluate this method call, then it will go into this method. So we now have a third segment in here. With a third table, a third context with stuff to do. Each method call will add a new segment. So this method call will complete, everything gets removed, and we get a return value in here, which will be evaluated and then returned. So we drop everything in here. And we return to here. And we use that evaluated value to determine if this block a equals 0 will be executed. So methods can be combined. This method is very special because that's our starting point. That's where our program starts. And you don't have the necessary knowledge to understand how that exactly works. So we'll slowly work ourselves up the hierarchy here. But for now, just assume we have all these methods that are all next to each other. All independent blocks of code, or mostly independent blocks of code, that just exist in any order. Doesn't matter in which order they are written. Whether they get executed or not, and in which order they get executed and how often, all depends on our code that calls them. If I never call the method, well, then it's just dead code in my program. And this code, and therefore also this code, will never get used. That's entirely possible. And a somewhat spoilery, not really spoiler, for the future. This memory view we have here, our little tables and these larger segments for each method. This entire thing, this entire memory here, is also called the stack. And it's one of two major parts of memory, though technically we should split it into threes at least. We kind of mentioned the other one. There is part in memory in here which just contains all your code and has tables for referencing different method names and whatnot. So there is a lot of definition and housekeeping that happens in your code that is part of the abstraction of C#, that you as the programmer, you don't get to see it, it's hidden away. So as far as you as the programmer are concerned, there will only be two types of memory. And this one, where we keep all our data for all our different methods and constantly call methods, we go down and then we go back once our methods are finished. This is the stack. And all our tables, everything that we did so far, always happens in one of these segments on the stack. And it's called stack because we slowly stack data up. I mean, right now you saw me always writing it down. Actually, we stacking downwards, inverse direction, but it's still building downwards, and then we slowly go back up and go down, back up and go down, depending on how many times we call a method. Whenever we call a method, we go one block lower, add a segment, and when that method is finished, that block gets removed and we go back up. That's why it's stack. We're constantly stacking these segments and removing them and stacking them on top. They always only interact with the topmost, or in this case lowermost, block. And that is all we needed to talk about today. It's a big topic, and maybe methods will take a bit of time to get used to, because there are some weirdish. Now there are also some really weird things we can do with that. And we'll have to explore a few more things next time. I'm not sure how much I'm gonna show next time, so maybe it will be sort of filler, where we add a lot of small things we lacked so far, that we just didn't consider. Right then, thanks for joining in, and see you next time.